couple years the SystemML, and they are so nice. They also open source the SystemML to public available, and they will try to merge it back to the Apache Spark community. So let's Fred and Steve talk about more in detail. Thank you.
Thank you, DB.
Yeah, thanks.
So thank you all for coming. Sorry about the little faux pas with the food, but glad we found it before we started. So please help yourself. Just a quick background about the Spark Technology Center. For those of you who are here for the first time tonight, which is probably most of you, do you have a good idea of what the STC is? Or is this all brand new to you and you're learning it on the fly? Quick show of hands.
No idea.
No idea. Okay, good. So let me give you the quick 60 seconds on it, and then we'll dive into the content. So back in June at Spark Summit here in San Francisco, IBM announced several big initiatives. One of them was the creation of this Spark Technology Center here on 425 Market Street. And what it is it's a community-first investment by IBM to help build out and enhance the Spark portfolio. So we're in the process of building out an engineering team. We're at about 40 or so people now here in the next couple of weeks. And we'll be investing to grow the engineering team to be several hundred over the next few years. And the intention behind that is to help IBM products basically re-platform onto Spark. IBM believes Spark is a disruptive technology that's going to have legs that last for multiple decades. We've done technology centers before twice in our history. The first one was around Linux, or excuse me, Java, and the second one was around Linux. And we do them when we believe that those disruptions are going to be so pervasive in the business that we want to make sure we have a role in how that technology goes forward in the future. So we've been partnering with all of the main players in the ecosystem, including Databricks. We're now a founding partner with AmpLab over at UC Berkeley. And we've started investing in Spark 1.4. We had 11 contributors in Spark 1.5. We're on track to grow that again significantly in 1.6 here at the end of the year. And as part of the big announcement back in June over at Hilton on O'Farrell, our general manager on main stage on keynote day one announced the open sourcing of the technology you're going to learn about tonight, which is SystemML. So it's IBM's machine learning technology that was built out of the Research Center starting about 8 years ago. And Fred Reiss is one of the key researchers behind that technology, so Fred will walk you through those details. Fred's background, he started with IBM back in 2006, right? Yep. And came from UC Berkeley where he received his Ph.D., so he's part of that entire community. He also has a family distinction, which is fun in the Spark community. He probably hates that I always say this, but his brother Charles is also one of the early Spark committers inside of the technology. So it's a very very smart and prestigious family with Fred and his brother. So we're very happy to have Fred on the team. He is our chief architect. And Fred is helping to spearhead a lot of the new technologies as well as integration of SystemML into Spark itself. So we're very excited about that. We are in the process, if you're interested, if you know anybody, we're looking for engineers, designers. You're here in the design studio, so IBM is bringing its big investment with design and engineering together to do new technologies. We're also looking for communications people, folks in marketing, so on and so forth. We're building a cohesive business, but we've designed it to be community first so that IBM can help shape that roadmap going forward. So any questions, please feel free to talk to us offline. We'll be hanging out in the back where all the beer is. And enjoy the talk. Thank you. Thanks, Fred.
Thanks for the introduction, Steve. And so as Steve said, my name is Fred Reiss. I work here at the Spark Technology Center, and tonight I'm going to be talking to you about SystemML. Now, SystemML is three different things. It's a system, that's the primary focus of this talk. It's also a research group at IBM Almaden Research Center, the group that I worked with prior to coming here to the Spark Technology Center. And it's a research project that was the primary focus of that group. So I'm going to start out by talking about the project itself, how that project came to be, what was the story, what was the motivation behind developing that project. Then I'm going to go and describe the system, in particular the core of SystemML, which is our cost-based and rewrite-based optimizer for machine learning programs. After that, I'm going to go into some of our more recent research work, adding a new component, a high-level resource optimizer to the system, to SystemML. At the end, I'm going to go briefly into what is coming next for regard to SystemML in terms of open source and Spark. And I'm hearing that the microphone needs to get closer to my face.
That's only for the camera.
That's only for the camera? Are we having trouble hearing in the back?
Yes.
I see. Okay, I will talk louder. So on to the first part of this, the SystemML project. And I should note, by the way, that for each part of this talk there is an associated conference publication, or in this case, this is a conference publication. Second part is a journal paper that you can refer to for more information. And you can find links to all these papers on the research group's homepage. Just search on Google for SystemML. The project, the SystemML project, started at IBM Research Almaden. I joined the project around 2013, but the actual roots of the project go back to around 2010, when we decided to start up a scalable machine learning group at the lab. And as part of working on scalable machine learning, we interacted with a number of different customers who had problems in that domain. There were about a dozen or as many as 15 customers, depending on how far you count an engagement getting along before it's actually an interaction. And they all had a kind of a similar shape. I'm just going to call out one example here to serve as an illustrative example. In this case study, we interacted with a major automobile manufacturer, a luxury automobile manufacturer, who had several sources of raw data, things like their maintenance reports, their warranty claims, information pulled from their cars. And they weren't really interested in doing big data analytics on this data per se. What they wanted was something that, a business result. They wanted to collect this raw data over to predicting the reacquisition of cars. In the automobile industry, it's very important to maintain customer satisfaction because most people buy the same brand of car when they buy their next car. So this company has a policy of reacquiring cars that are particularly problematic from a quality or maintenance standpoint. And when they're going to make that decision to reacquire a car, they want to make sure that they make that decision as soon as possible to minimize the damage to their relationship with the customer. So they're very focused on the business application here. They want to get from that data to there. Now, when they came to us, they had determined that they were going to extract out via various ETL processes a series of features and labels from this data, and then they wanted to do some machine learning. They had a couple different algorithms in mind to try and connect up to that prediction problem. Now, in the course of the engagement, we found a couple things. First of all, it turned out the initial set of features didn't have very strong predictive power, so we needed more features. And with more features and skewed data, the data set becomes a bit underdetermined, so you need more data points. And a lot of the algorithms that we thought initially would work did not work, so we had to iterate on a couple different algorithms until we finally found a path from the data to the result that the customer wanted. So you see a couple things going on here. The customer is focused on the business use case, and the characteristics of the data are changing even in the context of a single engagement, let alone over longer periods of time. Changing in several dimensions, in this case in terms of number of features and amount of data. And you have an iterative process to choose a good algorithm for analyzing the data. And this kind of pattern occurred across a number of different interactions with customers. And we thought about it and coalesced the pattern into something that we call domain-specific analytics. And that is where you have changes to the shape of the data in terms of the feature set, the size, changes to your choice of algorithm that require customization of off-the-shelf or textbook algorithms, and a process of quick iteration, all for the purpose of meeting a particular domain-specific analytics goal. This is the pattern that we see across many different customers. They need to be agile in terms of the machine learning that they're doing. That's not an off-the-shelf kind of thing. In particular, if you look at what we repeatedly heard from the customers, they expressed some requirements at their level over and over and over again. There are two phrases we heard repeatedly. The first of these is, my use case is different. And the second one is, I want control over my analytics. So let me talk about the first one. My use case is different. There are a number of different variables that go into determining a solution to a machine learning problem. A given algorithm is going to work well at a particular combination of data size, data sparsity, number of features, number of iterations, what kind of regularization you're going to do. Any combination of the variables that define this space is going to mean that you are working on a particularly narrow set of algorithms, and vice versa. So every one of our customers, even customers from the same industry, could legitimately claim that they had a completely unique machine learning problem. And furthermore, that this problem, the parameters of this problem, would change even as you were looking more deeply into the single instance of the problem. And so it's a moving target. And as a result of this moving target, we had this second statement we hear over and over again of needing control over the analytics. It's not acceptable for a IBM to come in and produce an end-to-end solution that works for the customer's problem and data as it was at the beginning of the engagement, because chances are that's not going to work very well at the end of the engagement, and it's going to work even more poorly a month or two down the road. The customer needs to be in control. They need to be able to change the modeling, change the feature extraction in response to changes of their business situation. Now, if you take these requirements that, as viewed from the customer and translate them down into something that an engineering team can understand, we get to these 4 different areas that a system needs to deliver on in order to be able to meet the domain-specific analytics kinds of use cases. The first of these, or rather the first 2, are about the characteristics of the language that is used to express the machine learning. We need a high-level semantics, so that we can express an algorithm at the level of an algorithm, not at the level of manipulating individual bits. But it's simultaneously, while it's high level, we need something that is expressive, that is flexible enough to cover a wide degree of different algorithms, because it's very hard to tell at the beginning of this exploratory process what class of algorithm you're going to come up with in the end. At the same time that we need this flexibility in describing the algorithm at a high level, we need a given algorithm to continue to work even as the characteristics of the data change along multiple dimensions. So first of all, the data and the scale. The characteristics of the data could include how many features you have, how many different types of labels there are, what is the sparsity, are you pulling things in rows or columns, how is your data structured. We also need to be independent of the scale. We need to be able to run the same algorithm at many different scales of data, because scale tends to change in the course of an engagement. Now, if you take these requirements that are pretty much the real-world requirements that we see for customers in verticals doing machine learning, and you compare them against what is available, what are the best practices, you can see that there is some coverage but not total coverage. In particular, the common best practice for doing statistics and machine learning today is to have a data scientist write scripts in a high-level data science language like R or Python with the SciPy extensions, or perhaps some other languages. Here we have a screenshot of SPSS Modeler, and run those programs on a personal computer. And these systems, as long as the data fits into the personal computer, can adapt within reason to the characteristics of the data, can run that algorithm that's expressed in a high-level language that's still powerful enough to cover many algorithms, and can get the job done. The trouble that comes into play here, the place where this does not work, is where the problem, the business problem, drifts to a point where it is no longer something that fits onto a personal computer, when it becomes a big data problem. In that case, you can't use this environment because the data will just overflow the capacity of the hardware that you have. And this is the only hardware that these languages will run on. Now, the current best practice for dealing with a situation that has rolled over into the big data realm is to fall back on having multiple different classes of specialty. You have data scientists, and they interact with systems programmers, people who specialize in making data science run fast on particular back-end platforms like Hadoop or Spark or NPI. And so the process is the data scientist may do some initial prototyping using a high-level language, but very quickly the problem turns into a systems programming problem. Now this approach gets the job done, and a number of very large companies have had consistent success with this approach. But when you get into a more vertical business, someone whose primary focus is not data analysis, but say, oil exploration or building cars, this gets to be problematic because first of all, it's difficult to staff up this kind of organization. Second, you have a lot of wasted work here because you're implementing every algorithm twice. And third, and probably most importantly, the process of doing domain-specific analytics is inherently an iterative process. You're not just going to go through building that algorithm once. You'll build a version of the algorithm, it will sort of work, you'll improve it, make another algorithm, and go through multiple iterations of the analysis until you have something that covers the current version of the use case. And in this model, there is an element of human communication in that loop, which slows down the feedback loop dramatically. It can take an order of magnitude longer to converge on a good solution when you have two people who need to communicate every time you change the solution. So our vision with the SystemML project was to make this case look more like the single machine case. And the way that we chose to do that was to borrow some technology, or rather some high-level ideas, from the database literature, from the database research world. In particular, we want to take something analogous to database query optimization and put it in between these high-level analysis languages and the different parallel and also single machine systems that can be used to run machine learning. Now, more specifically, the approach that we chose to take to realize this vision was to build a query optimizer for machine learning languages. At the top level of the system, we have several different high-level language front ends. Currently, we have a high-level language that looks like R, another one that looks like Python. We have the capability to expand to other languages, something that we've been looking into as future research. And those languages all get translated at the higher level of our system into a generic data flow representation that we call high-level operations. And it is over these high-level operations that we have a cost-based optimizer that performs various cost-based transformations to produce low-level operations, a generic representation of the execution plan, the physical execution plan, across a wide variety of different multiple execution environments, ranging from something that will fit on a laptop, to a large SMP, to a Hadoop or Spark cluster. The goal here is to provide the experience of coding in a high-level language with the ability to scale along many different dimensions to many different data characteristics so that we can close that loop and enable faster iteration. Now, the specific high-level languages that we do are powerful enough to implement many different kinds of machine learning algorithms today, and we continue to expand those languages. Here I have some pictures of our R-like language dialect, and in the context of two different algorithms. These are two variants of linear regression. The one on the top is using the direct solve method to construct a system of linear equations. And the one at the bottom is basically conjugate gradient by the trust region method with two nested iterative loops, the inner one doing small changes, the outer one doing larger changes. Now, I've thrown this up here primarily, the one at the bottom, to show that we can cover advanced algorithms with the particular subset of R that we have in our language. But for the rest of this talk, I'm going to be focusing on that first one, which, as you'll see, actually includes quite a bit of technical depth. So let's make that a little bigger and look at that three-line script. So briefly, the first line here is constructing the left-hand side of a system of equations, A times beta equals B. That we're constructing A on the first line by basically multiplying the observations, the features by themselves, by their transposed selves, to construct a covariance matrix. And the second line is doing a matrix vector multiplication to produce the other side of that system of equations. The third line is feeding that system of equations, which is, of course, much smaller than the input data, assuming your number of features is relatively small, to a solver. This is a very effective technique for doing linear regression as long as the number of features is relatively small. So I'm going to look at how you would manually code up this algorithm to run on Hadoop or on Spark. It's not iterative, so it's going to be, you're going to have roughly the same design constraints in both systems. And we'll do that in the context of these data characteristics at the upper right. So X has 500 features, 300 million observations of those 500 features. Our labels are the same number of labels. And we want to do a linear regression over this data. We have a cluster where it's a MapReduce cluster in this case, but again, same results would apply in Spark, where we have 3.5 and 7 gigs of memory for each of the map tasks and for the master, which we call the control program. So in this case, maybe it's not immediately obvious, but the key portions of this program from a performance perspective are the parts that are circled here in red, those two matrix multiplications. The first one multiplying a matrix by its transpose, the second multiplying a matrix by a vector. And it turns out that in MapReduce or Spark, with these data and cluster characteristics, we can do both of these operations quite efficiently. In particular, when you're multiplying a matrix by its transpose, that's effectively taking the dot product between all the combinations of the columns. It's a covariance matrix. And we can do that in parallel as long as on every node we can keep in memory a horizontal chunk of the matrix that's at least one block tall and covers the entire width. So we can do that in MapReduce context with one set of MapReduce, where map is going to take all the intermediate dot products within one row of blocks, and reduce is just summing up those sums. And it turns out, if you do this distribution model, there's enough memory left over that you can piggyback that matrix vector multiplication on the same MapReduce job or on the same stage of your Spark pipeline by either putting it in distributed cache or inside a broadcast variable. And then once you have those results, the XTX gives you A, the left-hand side of the equation. The multiplication with the vector gives you B, the right-hand side of the equation, well, B transpose, which you need to retranspose. And you can feed that into your solver. The system of equations is sufficiently small that it runs on the master. This is about as efficient an execution plan as you will get, at least in the context of a distributed system like Hadoop or Spark. You're doing one round of distributed computation over the base data and a small amount of cleanup in the master node at the end. So it's not going to get much faster than this. That said, you'll note that at several points we've been dependent on the data characteristics matching up with the cluster characteristics in the context of this algorithm, which leads me to ask, what is going to happen in the course of a typical exploratory process where the data characteristics change a bit. So, for example, let's say that the initial set of features does not have sufficient discriminative power, and we need to get another 1,000 features on top of our initial 500. Well, this changes the shape of our matrix X. It makes it wider. And with this particular combination of data and cluster characteristics, that means that a one block tall chunk of that matrix no longer fits on a given node. So that algorithm of computing a matrix multiplied by its transpose in one pass is going to run out of memory, it's going to thrash, and it's going to crash after a long period of time. It's going to fail. You need to fall back on a more conservative full matrix multiplication that's fully out of core. There are a couple different variants of that. Either of them will work. And then you can still piggyback the matrix vector multiplication on part of that. So that's one variation on how the data might change as part of your exploratory process. Now, perhaps you find that the input observations are very skewed towards certain parts of the data, and you actually need more observations. Let's say instead of 300 million, 600 million rows in your matrix. Well, in this case, the matrix X, your feature matrix, is same width, so we still can fit a horizontal slice of it in memory. Multiplying it by its transpose can be done in one pass. But that vector that we were piggybacking on that X transpose X multiplication now has gotten big enough that it doesn't fit in the remaining memory. So again, if we ran the plan on the previous slide, the system would run out of memory, it would thrash, and then it would crash. So you need to move that matrix vector multiplication to a separate job, to a separate stage of your graph, of your execution graph. Well, let's think of a third scenario. Imagine that you find of those 500 features you started out with, 400 of them are not very useful. So you're down to 100 features, and with 100 features you only need 1,000,000 rows to get a good result. Well, in this case, you've reduced the problem to something that effectively fits very well on one machine. And in this case, if you use that efficient multi-parallel execution plan, it's actually going to be an order of magnitude or more slower than just running the problem on a single node. So you really want to use a single machine when the problem gets that small. So I've walked you through a couple different physical execution plans for running this 3-line script. And the upshot of this is with 3 lines of code, we can show 4 dramatically different execution strategies and little tiny, moderately small changes in the data characteristics, the sort of things that you would expect to see in the course of an exploratory analysis process lead to dramatically different changes in plan. A plan that was optimal before becomes a plan that does not even run. So we have a lot of complexity here. And the question is, how could you expect a data scientist, someone who is an expert on machine learning but not distributed systems, to manage this complexity? The point of view that we came to the SystemML project with was we should not put that burden onto a data scientist. We should instead build a database-style query optimizer and let the optimizer handle that complexity. Which brings me to the second part of the talk, a description of the optimizer that we built around the high-level languages that we support. Again, there is in this case, a journal paper that describes this work in great detail. I'm going to cover just some salient points here. So recall from earlier that at a high level, SystemML has this structure. We have multiple high-level language front ends. Those high-level languages get translated into high-level operations, a generic data flow representation, which go through cost-based optimization, turn into a physical plan represented as low-level operations, which then get executed by a runtime. Now, this is actually a very cartoony version of the optimizer. The real picture looks more like this, and these are actually fairly complex boxes. I'm going to focus on just some of these here. You'll find a much deeper drill down in the journal paper. In particular, I'm going to be talking about some of the rewrites that happen in the high-level operations, or hops layer. I'm going to both static rewrites that are non-cost-based and rewrites that are cost-based. Also going to talk about the more cost-based portions of the optimizer, the translation down to physical plans, and the dynamic recompilation resource optimization that occur in a matter that is triggered by data characteristics and by our cost model. Now, before I do this, I'm going to try and contextualize this entire stack by walking through how a given program would get compiled and run. And I'm going to go back to the same program as before, our direct solve linear regression. Here I've added a little bit of a preamble, a small bit of what you would actually see in this kind of script, some stuff to read data in, to compute high-level statistics. The first step of compiling a program like this is to break it down into basic blocks. And then for each basic block, we construct a directed acyclic graph of high-level operations. We call this a hop DAG for short. Now, this directed acyclic graph goes through a series of rewrites, such as constant folding and algebraic transformations, which I'll show you in a moment. Here we're showing the DAG after those rewrites, because we want to get to the crucial cost-based portion of this stack, which is where we take that graph of high-level operations and we label it with data characteristics. Once we've propagated those data characteristics throughout, we can make a decision about which parts of the graph are going to be run on a master node and which are going to be spread out across a cluster. In this case, we call the master node the control program. This is the jargon of our MapReduce backend. In Spark backend, it would be running on the executor. And also the distributed computation here is labeled as MR for MapReduce. Obviously, that would be running in the drivers on a Spark cluster. Once we've made this decision at a high level about whether something is distributed or not, we have a further cost-based determination to make about what physical operator implementation we're going to use at the low level. And that produces the low-level operations DAG. In this case, we have the DAG that corresponds to part of that hop DAG, because a high-level operation typically translates into multiple low-level operations as we get closer and closer to instructions for our runtime. So in this case, we've got the hoptag for the operations that I talked about earlier, and that's translated down here to something that takes the matrix X of feature values and is going to feed that in to your transpose self matrix multiply, as well as to a map side matrix multiply with the vector Y. So this is the low-level operations representation of that execution plan I showed a few slides back. Now, one thing to note that cuts across all of this is we have what we call a hybrid runtime. Instead of running everything on the cluster, we maintain a single node SMP and cluster execution. And the optimizer is choosing which part of the script to run on the cluster and which part to run on the larger SMP in the driver. And this choice is very crucial to obtaining performance across a wide variety of data characteristics. Now, one thing that was not shown on the previous slide was, of course, the rewrites that happen when we're in that high-level operations phase of compilation. And there are quite a few of them. The exhaustive list we go through in the journal paper. In this talk, I'm just going to talk about two classes, the static and dynamic algebraic rewrites. So first, the static ones, which happen first in the chain. These all have the characteristic that they are a guaranteed win. They always make the program faster and when you perform these transformations. And you don't need to look at data characteristics to determine that that makes the program faster. You can see some examples up here. So if we see the program contains x divided by 1, we can replace that with x, for example. If we see the program takes the trace of x multiplied by y, we can replace that with just a simple aggregation. Right? So there are a number of these different patterns where if you translate them, they are a win-win situation. And some of these may seem a little obvious, but there are several situations that produce these patterns. First of all, there are a lot of cases where a script is written for a general case, but when you run it, because of constants, it turns into a very specific case. So you may have x divided by 1 might occur where you have x divided by the number of classes that you're classifying among minus 1. And if that number of classes is 2, then all of a sudden it's x. You can get rid of a distributed operation. Right. Other ones turn out as a side effect of other rewrites. And other patterns get triggered because it is more convenient for a practitioner to write something down in a particular way, even though that's not the most efficient way to execute it. The trace of x times y is a good example of that. You might see that written down in a textbook description of an algorithm, and you don't want to change it if you don't have to. Now, this is just some of the rewrites. We have a long list. And we continue to add to this list as we find general situations that cut across different algorithms where we can automatically speed things up. So again, these are the static algebraic rewrites, things that are always a clear win. In addition to these non-cost-based rewrites, we have a number of rewrite transformations that are done in a cost-based fashion. That is, we use the data characteristics and the known operator and algorithm characteristics to make an informed decision about whether it's better to do one thing or another. One example of this is our weighted squared loss rewrite and the associated weighted square loss operator. There's this common pattern of computing a weighted square loss that occurs in a lot of factorization algorithms that involves this summation you see up here. And the trouble with this pattern is that if you just execute it naively, starting from the inner loop, you end up materializing a lot of intermediates. And if the inputs to this pattern are sparse, as they often are, those intermediates can get very large because they are dense. Here's a pictorial representation of what's going on here. So if you were computing this naively, you'd start with the inner set of parentheses, multiply L by transpose R to get a dense matrix of this size. Subtract that dense matrix from here, you get another dense matrix of that size, which then gets multiplied by this to produce another dense matrix. So 3 gigantic dense matrices when your data is actually very sparse and small. That's not very efficient. If you find this pattern, you can implement it actually all fused together with what we call a weighted squared loss operator, which is going to iterate over the chunks of the final output and produce them one by one by probing into the sparse inputs. We basically do this entire expression in one pass. Now, the decision in the optimizer to use this weighted square loss operator instead of generating a plan that does the computation as written is a cost-based decision. We need to know what are the sizes of the input, we need to know what are the sparsities of the input, and of course we also need to pattern match on the structure of the code itself. So there are a number of other similar cost-based rewrites where, in addition to where the rule for rewrite is triggered not only on the existence of a pattern in the code, but also on these cost-based constraints about the characteristics of the inputs. Now, after we get through this rewrite layer at the top level of the optimizer, we get into something that would be more familiar to someone from a database background, that of a purely cost-based decisions about physical plans. And a good example of these cost-based decisions is the decision that we make when we have to generate a physical execution strategy for multiplying two matrices. We have a number of different kinds of matrix multiply that we implement in SystemML, and the optimizer needs to make an informed decision about which one to use in a particular case. And we make that decision based on characteristics of the data. There are some characteristics that will make certain operators possible, and there are other characteristics that will make one faster or slower than the other. So, for example, we have permutation matrix multiply. That is a specialized variant of matrix multiply for dealing with permutation matrices, matrices of ones and zeros that are used for pulling out certain rows or columns of other matrices. So the choice of this operator is actually interacts with the algebraic rewrites, because our algebraic rewrites, both at the high level and low level operations layers, will expose the characteristics of the input data, for example, partitioning, that will make various matrix multiply implementations possible. Here's a quick example. Again, it should be familiar. The second line of our linear regression script, where we're multiplying transpose x by y. Here's the high-level operations representation of that. We read in x in a transposed fashion. Well, we read and transpose it at the same time, and then multiply that by x. That's a binary arithmetic matrix multiply high-level operation. When we translate this down through the rewrite layers and the operator selection, we end up with this graph of low-level operations. Now, these are the result of both rewrites and the cost-based operator selection. Cost-based operator selection is producing this choice of matrix multiply operator, whereas rewrites are producing the other low-level operations around it that make the plan eligible for map-side matrix multiply, in this case the partitioning, the final aggregation on top of it. So we have a strong cost-based component in the middle of the optimizer, but it also interacts with the purely rewrite parts. So to tie this all together, I'm going to run through another example from beginning to end and show how all these rewrites interact, and then how we go back down into generating a plan. Here we have two lines from the middle of a multinomial logistic regression script. And these particular lines are from the inner loop. They're updating matrices that are used to compute the next set of coefficients for the next iteration. The particular semantics of what they're doing are less important than just the structure of this equation. So when we feed this through our parser and get it translated into high-level operations, we can then trigger a series of rewrites. And the first rewrite is going to take the entire right-hand side of that second line, and by folding constants, reduce it down to just the matrix Q. In this case, we have k equals 1. We are doing two-class classification with a script that was intended for n-class classification. Because of that k has been set to 1, a lot of things reduce just to nothing. So we can rewrite those away. Very important for performance. But the fun has only just begun. We can take the Q now and factor it out of here and here. And so now we're left with this pattern, 1 minus this expression times Q. And then another rewrite can look back up at the previous line. Actually, it's operating over the high-level operations so it will look higher up in the DAG, and take the definition of Q and substitute that in. And then from there, we can do some additional pattern matching, because this part happens to match the pattern for an efficient built-in proportional sum function, at which point we have generated a chain of matrix multiplications, which happens to fit into a dedicated matrix multiplication chain operator, which can do those chains very efficiently. And based on the data characteristics, the optimizer can make further decisions about where that operator gets evaluated and what's happening distributed versus not. Now, one thing that I've not talked about in discussing all of these cost-based aspects of the optimizer is what happens when you don't have good cost information, or when you don't have any cost information. A good example of this is what's in the middle of the screen right now. Here we have a snippet from a script for doing stepwise linear regression. This is a version of variant of linear regression where you're iteratively adding in different choices of features, perhaps because you have too large a feature set to begin with. So in the inner loop of this algorithm, we are calling the direct solve linear regression that I talked about earlier. But every time we call it, we're calling it with a different subset of the features. So that matrix X that contains the feature values is going to keep on growing throughout the execution of this algorithm. If we used a fixed plan for linear regression direct solve, that plan might start out correct, but it would quickly become wrong, or vice versa. So what we need is to make the system adapt itself to changing data characteristics in the course of running an iterative algorithm that actually changes the characteristics of the data with each iteration. And the way we do that is with dynamic recompilation. The strategy here is similar to what happens in a data warehousing context, where you may get partway through a series of bushy joins, and then the data warehouse engine determines that its initial cost estimations were off and re-optimizes the plan. But when you get down to the details, there is a lot of technology here that is very specific to the machine learning domain, and I'd encourage you to read the paper to find out the nitty-gritty details. I'll just talk about the high-level details here. So to implement dynamic recompilation, we have some hooks that happen in our compiler, our optimizer, and in our runtime. In the compiler side of things, we need to make decisions about what is the scope of re-optimization. When is the plan that we generate going to trigger re-optimization? And there are two decisions we need to make that plan trigger re-optimization properly. The first is what are the blocks that we might re-optimize? And the second is which ones actually will trigger re-optimization. And so the decision there is based not only on the control structure of the program, but also on what information is available and can be propagated forward from input data characteristics. Now, when the program hits one of those re-optimization points, what happens is we trigger a 5-step process. First, we create a copy of the execution plan, the high-level operations, so that we can make destructive changes to the plan, remake some decisions that we had made earlier about the execution. Then we update statistics based on up-to-date information. We redo any rewrites that are cost-based. We redo any computation of memory statistics now that we have decided what will be the low-level execution operators. And then we regenerate the instructions that will tell the runtime how to run that part of the program. Here we have a pictorial example at the lower right. This is a high-level operations DAG that implements the expression up there, x times p minus y, where x, p, and y are all matrices. You can see we are reading x, reading p and y, subtracting p from y, and then multiplying x by the result of that subtraction. And at the point in execution that we have reached in this picture, we have some statistics about the characteristics of these data items, which are all set to -1 because the system could not predict the sizes of these matrices ahead of time, most likely because they're intermediate data that may be the result of an operation such as filtering that could produce varying sizes depending on what its input is. So the optimizer will insert re-optimization points at points of the program that have this characteristic, and when we hit that point, we stop, we copy this graph of operators, and we look at the data characteristics and recompute, propagate up those actual sizes. Once we have accurate size information, we can then revisit more conservative decisions about how to execute something. Instead of running something in MapReduce because it is very scalable, we can see that the data is actually small and pull it into the control program. We can make more aggressive decisions as opposed to the default more conservative decisions and speed up execution of the program in the context of the more accurate statistics that we have here. And then once these decisions have been revisited, we just continue execution from that point until we hit the next reoptimization point. Now, the big thing to remember here is that we can do this reoptimization in milliseconds. So we have the ability, because of the way the optimizer is written, to be continually reevaluating the execution strategy based on up-to-date information about the data. So to recap, I've talked about the notion of declarative machine learning and how that is something that we have developed for the purpose of meeting the needs of domain-specific analytics. I've talked about the language and the compiler that we developed to implement declarative machine learning, and I've gone through some part of the internals of the compiler. Now, there's a lot that I didn't talk about in this first half of the talk, which you can find either in our existing publications or in future upcoming publications. In particular, we have several other aspects of the optimizer which go beyond the journal paper. For example, our optimizer for handling automatic parallelization of for loops. We have now a Spark backend which is not currently covered in our publications, but should be shortly. We have been working on low-level and other alternative distribution strategies for NUMA architectures, GPUs, and the like. And we've also been exploring what are the optimization ramifications, the query optimization ramifications, when the characteristics of the cluster are not fixed, when you can change those resource allocations. Now, this last part I'm going to go into a bit because, well, that's the third part of the talk. A resource optimization in SystemML. This is the optimizer that we built on top of our optimizer. And again, this is available in detailed form as a conference paper that was presented earlier this summer. So just to recap, I showed earlier how minor changes in data characteristics can lead to major changes in what is the efficient execution plan, or what is a possible execution plan. And a particular detail of this that I've gone over a couple times, maybe not in quite as much emphasis as we need now, is that we're talking about major changes in plan subject to the cluster configuration. Right? It's the combination of the data and cluster characteristics that lead to the change in plan. So in the work that I'm going to discuss, we're going to open up the possibilities for different cluster configurations and reconsider what we can do as far as optimizing the execution of a machine learning script.
So can I ask you some questions? So how do you
sure.
estimate the size of the data before touching it? Because
yes.
On the size of data
Mm-hmm.
in HDFS, that's often going to be different from the size of data in memory.
Correct.
Especially you do compression, or if you send in a CSV file. So how do you estimate it? Because your optimization engine, you don't know the size of the data.
Correct. So the question for those on the live stream is, how do we get accurate estimates of the size of the data in the first place? And the quick answer is that we piggyback that estimation on the first step of reading in the data that has to happen at the beginning of any operation. When we do the parallel read of, for example, raw data in CSV format, we are simultaneously translating it into binary for future execution and computing statistics on things like sparsity and dimensions.
Oh, so you need a one pass.
We need one pass, but remember that we have dynamic recompilation. So after we've done that pass, we can fill in the blanks in our what was previously a very conservative execution plan and redo the cost-based portions of our optimization.
So it's going to be in the next step.
Yes.
But for normal equation, right, you can solve it in one step. So
for certain problems, the execution is dominated by reading the data.
Okay.
And for those cases, no matter how fast you make the part after reading the data, it's not going to help much. But there are a lot of machine learning use cases where it's the iterative part that happens after reading the data that dominates. And that's where we're really targeting this optimization for. Yep. So great question. So I'm talking here about resource elasticity and optimizing the resources of the cluster for the characteristics of the analytics script and the data. And in this context, where we say the cluster characteristics are not fixed, this context can occur in several different scenarios. It could be because the cluster is actually running on top of a cloud and is dynamically provisioned. It could be in more of a shared cluster use case where you have a fixed set of machines, but they're used by many different people. These situations where you have flexibility in resources can even occur where you have one person using one cluster, because you have to make decisions about how much of the cluster resources to give to different parts of your distributed framework. Things like how big are your executors. So in this problem domain where we can change the characteristics of the cluster, where SystemML is in control of those cluster characteristics, we want to formulate an optimization problem where we're going to change not only the execution plan, but also the cluster characteristics to target those for the particular script and data combination. And in particular, we're going to frame this problem so that it's in the form of using as few resources as possible while getting the maximal performance out of the system. And the key aspect, as we'll see, that we need to address here is managing the two pieces of memory in a system like Hadoop or Spark. This work was done in the context of our Hadoop backend, because we didn't have a Spark backend at the time. But we're managing the trade-off between the two most important aspects of the cluster configuration: the amount of memory, because memory is a hard resource to time slice, that you dedicate to the driver versus the executor, or in our Hadoop backend to the control program, our analog to the driver, and to the MapReduce tasks. So we have chosen to use a two-phase optimization approach, where we have a separate resource optimizer that uses our one-shot plan optimizer as a subroutine. So the resource optimizer sits above the SystemML compiler optimizer and interacts with that optimizer and with Yarn in this case. And the way that this process works is, first we get some cluster information as well as some statistics about the program, about its input data from the SystemML compiler. This may actually come as a result of hitting a recompilation point, so we have the accurate statistics. And that starts the resource optimization approach. So using this info, we construct a resource optimization problem and explore different potential points in the optimization space. The resource optimizer is going to feed parameters into the compiler and get plans back and cost information back. And it's going to use our analytical cost model to estimate what would be the impact of different memory configurations of the two important memory aspects: how much memory is given to the driver, how much memory is given to the executors. And once we've made an informed decision based on this cost model, the resource optimizer then makes a resource request to Yarn in this case, which will then run the runtime. Now, the optimization problem that's getting solved inside this resource optimizer is maximizing the minimum or minimizing the maximum, depending on how you look at it. We want to find the configuration that uses as little memory as possible while getting the maximum possible performance, the maximum possible throughput for running the algorithm. And this, the equation here with the min in this case, is using our cost model, using our optimizer's cost model as a subroutine, as part of the optimization framework. So we have this white box cost model because we can look at the program, we can look at the data characteristics, and we can predict how much memory will be used at different points in the program and what will be the ramifications in terms of physical execution plans that are available with different amounts of memory. Now, to be able to solve this optimization problem, we need to construct a search space. And the way that we construct the search space broadly speaking, is to break the program down into chunks and to group those chunks together according to what data structures those chunks depend on being in memory. And once we've segmented the program like this, we basically have divided it up into waves of parallel execution. And for each wave, we need to pick what is the amount of resources that are dedicated to the driver node and to the executors. Because obviously you wouldn't want to change executor memory in mid-wave because that would defeat the purpose of chaining together parts of the program. But we do want to make that decision at multiple different points in time. So if we construct this set of constraints, we'll have one memory budget for the driver overall, because we don't want to restart the driver if we can help it, and a series of different memory budgets for the executors for different phases of execution. Now, the strategy that we use for solving this optimization problem in this paper was grid enumeration. Not a simple grid enumeration, but an adaptive choice of grid. Actually, we considered several different ways of generating the points of those grid parameters. And the one that worked best was using the statistics from the optimizer's cost model to choose key points in that parameter space and then querying the optimizer at those key points. This reduced the number of grid points that we needed to search in order to find a good plan. And we have further pruning strategies which cut down the number of grid points we need to query, that we need to compute the cost estimates by another order of magnitude or two. So with the kind of reoptimization cost that we have here, we can trigger resource reoptimization at nearly every normal reoptimization point. So we have the ability to actually very quickly, dynamically move the cluster to a different configuration, at least for its parallel execution. Now, so that's a very high-level picture of how we do automatic resource optimization. There is a question.
Yeah, so
yes,
I was just wondering whether you have run these algorithms on the Spark side
and
compare with the Spark's dynamic resource allocations.
That is a very good question, whether we've run this on the Spark side. We have done some experiments with Spark as part of this paper. They were done with a very early version of our Spark engine, though. And we're looking into a more advanced version of this that's really fully end-to-end on Spark, that's going to incorporate our ongoing work on automatic management of caching. But that's in the future at this point.
I'm just wondering,
so,
because the Spark,
yes.
the things 1.2 or 1.3 already include this dynamic allocations, which you can set the number of executors and
yes.
of course, and then dynamically increase as you need it.
Correct.
So how that compare with your, essentially you do a pre-optimization first and then set it and don't change it during that process.
Right. So again, for those on live stream, the question is, how would this compare against the dynamic on-demand allocation of executors with fixed chunks of memory? So in some cases, you'd get the benefit of that approach with this, but you have to remember that our optimizer is choosing a strategy that best uses the resources that are made available to it. If you tell our optimizer to choose the lower level optimizer, I should say, if you tell it to choose a plan that's going to use, if you hand it the whole resources of the cluster, it's going to try and use them. So, and the same kind of goes for a lot of algorithms that are even hand-coded. So it may be better to choose a different execution plan that is more constrained in its use of cluster resources, depending on what is the cost of getting those resources.
I think as Spark essentially, you say, for example, I don't know how many number of cores or executors are going to use and how many memories each one going to be. I mean, it's set as minimum, let's say, one core, 1 gig or whatever, and then as the data goes along and the jobs goes along, say, oh, I need more, and they just allocate more.
Right, but the issue is that your choice of implementation for the steps of the algorithm can use more resources than you necessarily need to get good performance. And we're leveraging that fact to get better numbers here. So, but we should talk offline about this at greater length. A very interesting conversation. So I was talking about our experimental setup. Now we did a two-round experimental evaluation here. In the first round, we were looking at the question of is it a good idea to use our analytical cost model to make these resource decisions? And we set up a Hadoop cluster, because this was on our Hadoop backend, configured as we describe here. This is basically a standard cluster with 2 U servers, 6 machines as worker nodes, 1 smaller head node. And we ran a number of different algorithms. These are 2 variants of linear regression, support vector machine training, multinomial logistic regression, and generalized linear model. All of these very long scripts, much more complicated than anything I've shown on the slides here. GLM, for example, is in the hundreds of lines. And we ran them over several different combinations of data characteristics with generated data. And we compared the resource allocation chosen by our resource optimizer against several different fixed allocations of memory. And on these graphs, we see the execution times of chosen algorithms on particular data sets. There's a full set of graphs in the paper, obviously. And the high-level point here, blue is our optimizer, red is the fixed plans, is that even though we're using a approximate analytical cost model and not true costs, we can make decisions that get very close or and sometimes beat the best static allocation of resources. And the difference between the best and worst static allocation of resources can be quite severe, as much as an order of magnitude, either because the system might decide to do something in parallel that would be better done in main memory by having more memory go to the driver, or because if you give too much memory to each executor, you have fewer executors and you cannot take advantage of the compute of the full cluster. Or in some cases where you just need to pick the right execution plan to handle large data, which is going to be both large in terms of your both parts of the memory budget.
Okay, another question.
Yes.
So, suppose based on your cost optimization, you set to say, okay, this is the best plan, best setting for the memory, and then you start running.
Yes.
The job takes a long time to run, and during that time, because the cluster is used by other users, they essentially steal the resources you're going to use. So
Yes. So the question is, what happens if other users steal the resources you are using during a long-running job? In this particular case, we're running on Yarn with reserved resources. So you wouldn't have stealing happen. What you might have happen is when you hit a re-optimization point, there will be fewer resources available. So you have a different optimization problem. And since we are recomputing statistics, both from the Yarn master and from the optimizer and its data statistics, at each re-optimization point, we can make that decision in the context of the current state of the cluster, even if that state has changed. But this question is really helpful at this point because it gets me into actually the next set of experiments. Because if you squint at this data and look very carefully, you'll see that there actually is one static allocation of resources that does quite well overall. Gets the wrong answer a couple times, but gets the right answer about 90% of the time. And that is basically allocate all of the cluster's resources, as much memory as possible, to running your script. Have a really big driver and a bunch of really big executors that use up all of the available memory. As long as you're the only one on the cluster, that's a pretty good plan, but that is a problematic strategy in practice, partly because if you are renting the cluster, you have to rent a larger cluster, but more importantly, because if there are other users on the cluster, tying down big chunks of memory is going to kick them out, is going to make their experience considerably less positive. And in this second set of experiments, we modeled this use case. We ran multiple copies, in this case of our linear regression script. We also tried this with other scripts. Multiple copies of the same script at the same time, modeling a use case where multiple users were doing machine learning algorithms on the same cluster, or perhaps where one user is running many algorithms at the same time. And we looked at the overall throughput in terms of jobs executed per second or minute, measured in 2 scenarios. The red is when we have a fixed allocation of cluster resources to each job, a large executor, large drivers. And the blue is where we use our resource optimizer to dynamically choose how much memory we're going to pull. So to try and pull the minimal amount of memory that still gets maximal performance. And what we can see here is as the offered load on the cluster, as the number of simultaneous jobs goes up, the case where we are grabbing a conservatively large amount of memory for each job starts to plateau. You reach a point where you cannot fit additional copies of the script onto the cluster, and throughput suffers. Whereas with the dynamic resource optimization, which can look at the data characteristics and choose a smaller, more aggressive amount of memory, we can more fully utilize the resources, the compute resources of the cluster. So I've talked about the motivation and the design of the project, the optimizer at a high level, and also the optimizer on top of the optimizer. Now in the next few minutes that remain, I'd like to talk briefly about what's next with the project. The first thing that's next, and I've kind of alluded to this throughout the talk, is we now have a Spark backend for SystemML. Our optimizer can target either Spark or Hadoop MapReduce. In both cases, it's a hybrid backend that dynamically shifts computation between a distributed shared nothing execution and a SMP mode of execution. We started this in late last year. At this point, we're pretty much feature complete. We can run all of our different algorithms on Spark. We're still doing some performance tuning, but if we look at preliminary performance results, they are very promising relative to our Hadoop backend. In the sweet spot of Spark, in this case with about 160 gigabytes of data, something that fits comfortably into aggregate cluster memory, we can get speedups of as much as an order of magnitude on the Spark backend compared with Hadoop, because with Spark and iterative algorithms, we're able to cache, in this case, the entire data set in main memory. So we can iterate a lot faster. When data goes out of core, we still surprisingly get a speed up, because even though the main portion of the data no longer fits in memory and has to be streamed from disk, we can still cache things like small vectors that are multiplied by that data in memory, and we don't have to continually reload them from distributed cache. So there even is a moderate speed up from using Spark in cases where you would think the cases are actually ones that favor Hadoop, because it's a more mature system for these large batch, large data, small memory situations. So
do you
yes.
benchmark against the MLGIF implementation of this algorithm?
Yes, and it's an ongoing effort. I'm not showing results of, the question was about benchmarking versus MLlib. We have been doing that. The results at this point have been ambiguous because we're comparing two different algorithms. We need to calibrate our measurements to the point where we are comparing apples to apples. Right now, the preliminary results are you can get a worse answer in less time, which is not beneficial. We want to calibrate so you're getting the same quality of answers and comparing time, but we're not there yet, so I don't have numbers here.
Okay, let's talk about it offline.
Definitely, a very good topic to talk about. So the second thing that's happening in the future, yes, Steve? Is there a question? Oh, sorry about that. Didn't see it.
On the topic of MLlib,
Yes.
similarly, do you package any of these algorithms for people to use, or is SystemML more of just you're writing your own algorithms and it will optimize it nicely?
Well, the original goal of the project was to make it so people can write their own algorithms, but in the course of a number of engagements, we've accumulated a library of 20 or 30 algorithms, and we ship that with the code. So if you go to our GitHub page, you'll get all of the algorithms along with the system. So today you get a bit of both. You get a language, an optimizer, and a set of canned routines that you can use to do different kinds of analysis. And the real benefit of having these algorithms shipped is not so much that you get yet another machine learning library, but two things. First of all, you get a library of machine learning routines that are adaptive to data characteristics, as opposed to specialized for sparse data, say. And second, you get a library of machine learning routines written in a high-level language which you as a practitioner can modify. So if you need a slight variation on our linear regression by the conjugate gradient method, you can go in and change the way we do regularization, and it's a very small change. And the optimizer is still going to be able to take your script and use it as before. So very good question, thank you. Which segues me into, conveniently, the open sourcing of SystemML. This was announced, as Steve mentioned, in June by Beth Smith, our general manager, on the stage at Spark Summit. that we're going to open source this technology, put it out into the Spark ecosystem, and hopefully incorporate some of these things into Spark. The project went live on GitHub at the beginning of this month. You can go to the URL at the bottom of this page. It's just github.com, SparkTC, that stands for Spark Technology Center, and SystemML. And you can download the code. There are instructions there for compiling and running the code. And as soon as we're complete with our current round of performance testing and tuning with the new Spark backend, we're going to put out binary releases at the same location, so that you can download a fixed release as opposed to getting a daily snapshot of the code. So with that, I'd like to thank everyone for coming. I really appreciate you coming out here on a work night and listening to me talk for over an hour at this point. And if we have any more questions, I'd be happy to take them at this time. So great. Thank you. So let's get some questions from over on this side. I'll start here.
Sure. So given that you have all the data and the metadata there, and you're working with a subset of the languages R and Python, is there any thought to making like a dependently typed Python or a dependently typed R, where you run it through a type system, you're able to like give people feedback as to whether or not they're pulling a missing column or that sort of stuff?
The question is whether we can have a dependently typed Python or a dependently typed R, where our type system incorporates other aspects of the data and can do checks.
Yes.
We actually do a bit of that behind the scenes, but it has not been a primary focus at this point. It's a very interesting area, and we are getting some more into that direction with some of the whole program analysis that we have started to do. We'll see where it goes in the future. So I have one in the front, but there were two people who raised their hand earlier. So let's move around here and then come around. So please.
Is it
Next.
possible to track changes between plans? Because, for example, let's say you start off with 100 megabytes of data, then 200, 300.
Mm-hmm.
Is it possible to track the changes between the plans and to maybe figure out bottlenecks in your cluster, for example, which might become a problem in the future?
So the question, again, for the people on live stream, is it possible, as you execute the plan and change the plan at re-optimization points, to track those changes in the plan and see if there are bottlenecks in cluster execution? At this point, we do pull in a lot of telemetry when running a script. Telemetry at the level of our low-level and high-level operations, which can be very helpful for someone to figuring out why the script takes as long as it does. We're not doing anything in an automated fashion to really reverse engineer what's happening on the cluster at this point. It would be an interesting area of future work, particularly as it plays into the resource optimizer. So we could detect that we have errors in our analytical cost model with respect to a particular script, or if the cluster is not behaving as we would expect it. That's a very interesting area to explore. So thank you.
So let's take one more question.
Okay, well, I'll handle your question offline. It's okay, but please, thank you.
Thank you. My name is Sadat. Amazing talk. Thank you for doing this.
Thank you.
My question is along the lines of the first question. How difficult would it be to write different language extensions for other languages?
So the question is, how difficult would it be to write other language extensions for other languages? The difficulty of incorporating a given language dialect depends on how well it fits into our high-level operations model, which is a general data flow representation that was initially targeted at our programs. But you need to have variables, a series of algebraic operations that you can do on them. The program needs to be roughly straight line, at least in terms of the semantics. You need to have operational semantics. Although obviously when it's translated into high-level operations, it turns into more of a declarative semantics. We have been playing around with the idea of a Scala dialect, for example, particularly for Spark integration. And we haven't seen any problems with that. For graphical languages, it's actually an easier fit, if anything. If you wanted to get into aggressively functional languages, that might be a bit more of an effort to get on there. But for the kind of more procedural languages that are common in the machine learning domain, we have a pretty good fit with the existing model.
And are you guys looking at accepting contributions for something like that?
Very much so. We would be very happy to have contributions to the SystemML project, and we really want to get outside contributors. Again, here's the URL. because we're trying to turn this into an Apache project, and that absolutely means we need non-IBMers working on this. So thanks again. Thanks everyone for coming. Really appreciate it. If you have additional questions, I'm going to stay around here for a while.
So
Thank you.
Thank you, the speaker again. So I
okay.
want to announce the following event. So on October 20 at Netflix, professor from Stanford called Joel Lavatsky, and he's also the chief scientist at Pinterest. He's gonna come to Netflix to talk about their recommendation system. So if you are interested in Pinterest recommendation system, please come to the meetup. And also on October 13, we're gonna have a GPU talk at App Dynamics in San Francisco. So thank you, speaker, again.
So
my
thank you for
question
coming. Yes.
was that about the high-level language that you're going to expose to the user. Perhaps the user will want to tune some of those decisions that the system will make behind the scenes about cluster plans or other